Good morning, everyone. This morning, I would like to present you the results of our research project where we developed a risk-based framework for fire safety in car parks and where we also performed 60 fire tests looking at the interaction between sprinklers and smoky heat control. FESG is a consultancy firm specialized in fire safety engineering. 2009, we started as a spin-off of Ghent University, and today we are 18 fire safety engineers working on building, industrial, and infrastructure projects. When we look at the consequences of a fire in a car park, we know that the outcome will be dependent mainly on two timelines. The first one is how quickly the fire is able to spread to multiple cars. And the second timeline is how quickly the fire brigade will be able to put water on the fire. Whenever these major fires happen, there's a lot of discussion on which type of safety measures should be in place. When we look at some recent trends, we see that more SUVs or larger vehicles are being sold, and we also see a clear trend on more electric vehicles. The last couple of years, there's also been a clear evolution in knowledge. 2010, FESG participated with Ghent University to perform more than 100 fire tests on pool fires and large-scale fires, where we compared the experiments with numerical simulations, and we got a good confidence in CFD calculations to predict the smoke spread. Now, combined smoky heat control and sprinkler systems were outside of the scope, and not much research had been done up till today. There's also clear evolution in fire brigade intervention. When we look at the beginning of the 2000s, almost no fire brigade corps had a thermal imaging camera. When we looked at the fire tests that we performed in 2010, 2011, the larger Belgian fire brigades had thermal imaging cameras, but not the smaller fire brigades. If we look at 2018, when we started this research project, there was new questions. Every fire brigade corps at that point had thermal imaging camera. It was part of their standing operating procedures. There was questions like, would sprinklers have a negative impact on the thermal imaging camera? Is it still required to have a smoke-free access when the car park is sprinklered? And then more general, what is the interaction between sprinkler and smoky heat control? Do they affect each other in a positive or a negative way? So based on that, we decided to start a research project, cooperated with Ghent University. We had a strong focus on the interaction of sprinkler and smoky heat control, where we performed 60 fire tests. And we developed the fire brigade intervention model specifically for car parks. The research was partly funded through VLAIO, which is the Flemish government institute for research and development. So in the next 25 minutes, I would like to discuss briefly the history of how the standards came about. Would like to discuss the development of the fire brigade intervention model, and then look into the results of our fire tests. Okay, so let's have a quick look at some of the legislation and standards. So looking at the history, since the beginning of 2000, you can see two types of legislations. You have some countries who have a culture of putting smoky heat control requirements in the legislation, like UK, Belgium, and the Netherlands. And then you have countries who have a culture of putting sprinklers in the legislation requirements, like Norway from 1300 square meters and Sweden from 5,000 square meters. Now, the countries who have a culture of starting with smoke heat control have been confronted with a recent trend when to add sprinklers and how to dimension smoke heat control systems if you add sprinklers. In order to understand the status, let's have a quick look on the standards. The first option would be to put a smoke heat control system in place, which would be designed on 2 or 3 burning cars. So basically based on the fire detection, which could take place between 1 and 5 minutes depending on the type of detection system, the requirement would be to have a smoke-free access up till 15 meters of the burning car for a period of 15 minutes. So if the fire brigade intervenes in the first 15 minutes, there is a smoke-free access till 15 meters. If the fire brigade arrives later, there is no requirement in terms of smoke-free access. Second option would be to put a sprinkler system in a car park where, according to the European standard, you would look at a risk classification of ordinary hazard 2, where the sprinkler would be dimensioned on 4 sprinkler heads plus a redundancy of 8 sprinkler heads around it, and based on that you would dimension the sprinkler. Some jurisdictions would allow for a smaller risk classification OH1 if the car park is of limited size. The question is what to do when you have both a smoke heat control and a sprinkler system. Basically, you would still need to put your sprinkler system in according to European standards, and then the smoke heat control, according to the standard, would still require a smoke-free access till 15 meters. And the question is it really necessary to have a smoke-free access till 15 meters, knowing that the average temperature would not be above 40 degrees? And second question is it really necessary to have a smoke-free access, knowing that the fire would not spread once the sprinkler is activating? Now, in order to compare the different safety measures or to compare the safety levels of a car park equipped with a smoke control system or a sprinkler, we need to step away from the standards and look at a risk-based framework. So we decided to apply the fire brigade intervention model to this problem. So the fire brigade intervention model is basically comparing 2 times, as we would do in an A-set, R-set calculation for life safety, where we would say everybody needs to be evacuated before you have untenable conditions. Here we would say the same. The fire brigade would need to be able to intervene before the fire has become too large. So we basically compare 2 times. The first time is a time for successful intervention, and the second time is the time till untenable conditions. Now, both of these times are depending on a lot of parameters with some uncertainties, so we're not talking about one specific time, but representing a distribution. Same for time till untenable conditions, basically how quickly the fire spreads, and from which time the fire is too large to intervene. And so what you see here is the overlap of both distributions, and that's the residual risk that by the time the fire brigade wants to put water on the fire has become too large and they cannot intervene anymore. So let's have a closer look at the first part, the time for successful intervention. So when looking at the timeline from the beginning of the fire till the time that water is put on the fire, we have a number of factors. First one would be detection and notification system. So depending on the type of installation, you would have a timeline between 1 and 8 minutes to cover both the detection and the notification. Then you have the response time with the dispatch. It's based on statistics of the Belgian Fire Brigade. Then you would have the travel time. After that, you have the time required to set up the equipment arrival at the site, looking at the intervention scenario, where to enter the building, etc. And then lastly, you have the attack, or walking down the staircases, walking in certain zones that are smoke-free, light smoke, or challenging smoke where radiation plays a role. So looking at the timeline, we see that in the best case, we would be looking at something around 15 minutes, and in the not worst case, but realistic case, would be around 40 minutes, would be exceptional. Now, the way this has been set up is that basically for each of these times you have certain distributions. So the response time for in Belgium is depending if it's a professional fire brigade or if it's a volunteer firefighters. The travel time, obviously, depending on the distance from the fire brigade till the parking, and then the attack time, walking speed based on the smoke conditions. When adding all the different parts of the intervention, you arrive to a total intervention time, which could be short in the order of 10 to 15 minutes, or could be in the order of 20 to 25 minutes, depending on the specific case of your car park. So that gives you the first distribution, time for successful intervention. Now let's have a look at the second distribution, the time till untenable conditions. So here we will look at the heat release rate for one car. So basically we looked at a PhD work of Dr. Tohir and implemented the models he had developed there in this framework. Basically he subdivided cars in 5 categories, from smaller cars to larger SUVs, and he looked at the probabilistic distribution of how the fire could evolve. So basically you have the 5 percentile and the 95 percentile here for a smaller car. So if you burn the smaller car 100 times, for 5 fires the heat release rate won't be larger than 500 kilowatt, and in 95 of the 100 fires it won't be larger than 4.5 megawatt. And the same for larger vehicles. So the higher the mass, the higher the total fire load, and also the higher the heat release rate, as it's mainly driven by size of the windows, as we will see in a minute. The second part is the possibility to predict the fire spread to adjacent cars. So basically a simple radiation model that will determine, based on the distance to the adjacent cars, how quickly the fire could spread to second, third, etc. Number of cars. So the interesting thing about this approach is that we're able to objectify the results. Instead of saying we assume that the fire brigade will arrive at 15 minutes, and we assume that the design fire is not higher than 8 megawatts, what you're able to do here is say, well, depending on the time of arrival of the fire brigade, we're going to look at what's the distribution of the heat release rate. So assuming the fire brigade arrive at 30 minutes, we know that there's a 5% chance that the fire is not higher than 4 megawatt. There's a 50% chance the fire is not higher than 13 megawatt, and there's a 95% chance that the fire is not higher than 27 megawatt. So this objectifies the results in a way that, depending on the time of arrival of the fire brigade, you can say what's the probability of failure of the smoke and heat control system. For instance, looking at the temperature at the shaft. So saying that if the fire brigade arrives after 30 minutes, there's a probability of failure of 50%, while if the fire brigade arrives after 15 minutes, there's only a probability of failure of, let's say, less than 5%. So pretty interesting to link both. Now, in order to apply it to a real case study, not going to go in detail, but basically you look at a car park where either you put a smoke heat control or you put a sprinkler system based on 6 heads, so OH1 instead of OH2, and you compare the safety level. Then you have the first distribution, that is the distribution for fire brigade intervention. So the red curve will not change in both options, but the distribution for fire spread will be significantly different in case of a sprinkler system compared to a smoke heat control, and that will result in a residual risk that then you can compare between the sprinkler and the smoke heat control system. Now, what's really important is the reliability of the components. So whenever you can connect your sprinkler to the water main, the reliability becomes higher because there's less components that could fail or valves to be in closed position. Now, we're going to get back to this in a couple of slides, but there's two crucial factors that you should think about when talking about effectivity of a system. One is the reliability, so the probability that the system activates when required, and for instance that water comes out of your sprinkler. For that you can have these fault tree analysis. Second one is the efficiency. So the efficiency is the degree to which a system reaches a certain performance, assuming it activates. Now, in order to say anything useful about the efficiency or system efficacy of a sprinkler system, we need to perform fire tests. So this leads to the test campaign where we performed 60 fire tests. We basically built a 70-meter long representation of a car park out of containers. As you can see here, we had about we had 3 containers where we could put 3 cars, so the burning car and 2 adjacent cars, to look at the fire spread. This zone was also equipped with sprinklers. Then we had containers on the upstream to look at the smoke spread upstream and then downstream. And here we could position a fan. So looking at the sprinkler layout, basically the middle car was the one where we would always ignite the fire on the passenger seat. The window of the driver's seat would remain open. And basically we had 2 setups, either the red sprinkler system with sprinkler heads on these positions, or the blue sprinkler system with the sprinklers in between the cars would be activated. We had water flow measurements, etc. We had a lot of thermocouples in place, velocity measurements in place, and thermal imaging cameras. The type of tests we performed, the first series was to look at changing the ventilation and look at how it would affect the sprinkler efficiency. Looking at the interaction also between sprinkler and ventilation. Second series of tests was to do tests with a reduced flow rate for the sprinklers, looking if we would witness fire spread to adjacent vehicles or not. And then the third type of tests were with higher activation temperature of the sprinklers, and then look at potential fire spread. Okay, so let's have a look at a test where there was a sprinkler system with no ventilation. So we're looking from thermal imaging camera. Let's start the test. So the fire was started with a wood grip on the passenger seat. The window of the driver's seat was open, and we're aiming the cross you see, the black cross, is a temperature measurement of the smoke plume coming out of the driver window. So we see a temperature around 160 degrees of smoke coming out of the driver's window. You see the heat accumulation in the container. So at this point, there's no visibility without the thermal imaging camera. And at around this stage, the second window, so the one of the passenger seat, will break. You see here the debris, and little time after the breaking of the window, we'll have the sprinkler system activate. So if you look at the temperature, you can see that at this time the sprinkler has activated, the heat reduction takes place, or the cooling takes place, and in a matter of 20 to 30 seconds, you see how the maximum temperature of the smoke coming out of the window of the passenger seat is around 60 degrees. But more importantly, you see that the average temperature is not above 40 degrees. So this was the results of a fire test with sprinklers with no ventilation. Nice to know, it was a sprinkler not dimension based on ordinary hazard 2. It wasn't dimension based on 12 heads activating simultaneously, but it was dimension based on 8 heads activated simultaneously. And still really good results where during the tests 2 or 3 sprinkler heads activated. Now let's compare this. Okay, interesting to compare now to a second test where we had combined longitudinal ventilation around 1.5 meters per second and the sprinkler according to the standard ordinary hazard 2. And let's have a look at the interaction. So what we see here is that the sprinkler droplets are visible on the downstream. So you can see the droplets coming down, but you also see that they don't have an impact on the tilted flame. Basically, the ventilation makes sure that the maximum heat release rate in the burning car can still be obtained, and it's a total different situation, ventilation and sprinklers compared to sprinklers alone. So basically, you have an advantage that you have a smoke-free access, but the disadvantage is that you have much higher heat release rate, higher temperatures, and that the efficiency of your sprinkler is much lower. So when we look at the sprinkler efficiency, basically there's 3 factors that play a major role for a sprinkler without ventilation. First one is that it avoids the external flaming. Second one is that the heat release rate inside the car is much lower due to the mixture of smoke and water vapor instead of fresh air. And the third one is that the water on the adjacent cars will reduce the probability of ignition. Comparing this with the sprinkler with longitudinal ventilation, we've clearly seen that there is external flaming on the downstream. We've seen that the heat release rate is much larger as you have fresh air being supplied instead of smoke and water vapor mix, and the probability of ignition is still reduced as the adjacent cars are being wetted, even though they see a larger thermal flux based on the external flaming. So if you look at the maximum heat release rate that you will get in a burning car, we see that you could have 10 times larger heat release rate in a burning car with combined sprinkler and smoke and heat control system compared to only having a sprinkler system. So having a high heat release rate, because you want to have a smoke-free access till 15 meters in a combined smoke control and sprinkler case, is basically bad engineering. What you do is you create a higher heat release rate by imposing a higher velocity. So when we're looking at smoke and heat control systems in sprinkler car parks, what we should really be looking at is imposing a maximum velocity instead of a minimum velocity. So we started with the fire brigade intervention model and then added the efficiency from the 60 fire tests, and we developed software to incorporate all of those aspects. So on the left side, you see the first version of the software, and more recently we developed a web tool so that more people could be using it. So in case you're interested to try it out on a design project or on a fire investigation project, please get in touch and we'll be happy to help you out. One of the important questions is it possible to treat new energy carriers? And in the software, we have the possibility to say what car type composition you have. So we have the possibility to add electric cars. The difficult part, though, is that it's really hard to find data about fire frequency on electric cars. Some publication will claim that the risk is lower than for traditional fuels. And so, although it's possible to incorporate it, until we will have more data, I'm not sure if it's useful, because the fire spread mechanisms might not be so different, and the fire brigade intervention model as is could be influenced either by hit release rate side, so how quickly the fire spreads, or by the fire brigade intervention. Now, when having discussions with Belgian firefighters, their point of view was that there was no difference for detection, notification, response time, and travel time, obviously. But then even the arrival at site and attacking the fire, they would use the same standard operating procedure. So there wouldn't be an additional time there. So I think that's probably going to be interesting in the coming years, when more experience about real interventions will be gathered from electric vehicles. We'll be able to see if we can incorporate that in a specific way in the fire brigade intervention model. But at this stage, based on discussion with the Belgian fire brigade, we haven't seen the need to modify anything on the fire brigade side, but would be happy to discuss it with any of you if you have some input on that. So we're at the conclusions now. So the fire brigade intervention model objectifies the residual risk. So basically, it's a performance-based framework which looks at the timeline for fire spread and compares it to the timeline of fire intervention, and it also includes the efficiency and reliability. As we've seen in the fire tests, often less is more. So for sprinkler design, what we've seen is that designing based on 8 heads instead of 12 would allow you to connect the sprinkler to the water main, especially in the residential buildings. Could be a big impact on the reliability. So increased reliability by a more simple system could be positive for the total effectivity. In fact, you have to think of it as ESFR type of function. You only want to have water on the burning car and on the adjacent car. You don't need to have sprinklers activating on 144 square meters. So you could increase the temperature of the sprinkler activation, or you could dimension it as a ESFR type. Second aspect is the smoke control system. When there is a sprinkler, basically the design should take into account the maximum velocity instead of minimum velocity, which will increase the sprinkler efficiency. Practically speaking, we should be designing smoke control systems on a smoke-free axis till 50 meters, for instance. Or you could even think about smoke clearance type of smoke control systems. But having high ventilation, high velocities will clearly have a negative impact on your sprinkler. So it's a choice to be made. And it's not one that will be made on standardization level. I try to explain it to the standardization of smoke and heat control. I think they like to put in large fans. Not sure if they understood the results or if they just didn't want to modify it. But I would definitely recommend not to have such high velocities in combined smoke control and sprinkler installations. That's it for what was my presentation, and hopefully you thought it was interesting. Thanks for your attention, and if you have any questions, happy to answer them now or later if you drop me an email. Thanks.